I've entitled this Engineering a Well because it's a unique well situation. Everybody out here where I'm at has city water, city sewer, uh, electricity from an electrical co-op. So it's not like we have water wells or anything like that. But way back in the day, there were hand-dug water wells, and this is what this represents right here. We'll get into this in just a second. This well was probably dug around 1900 or thereabouts. And from ground level to the top of the water is about 15 feet measured with a tape measure. There's about 6 feet of water in here, and then you have rock, sand, and gravel. The water in this is clear. You can easily see through it. It is not drinkable, but it can be used for watering plants, which is what the guy uses it for. He has a hand pump up here, has a board up here with a hand pump on it, and he pumps the water into a pitcher, and then he goes and waters the flowers with it. But he has become increasingly concerned about pets and or grandchildren falling into the well, and what he wants to do is he wants to fill this thing in but keep the source of the water for his plants. So since he has arthritis in both hands and is unable to do the work, he asked me if I would build him a well screen. What he originally had wanted was for me to take a miter saw with a super thin blade and cut thousands and thousands of slits across a piece of PVC pipe, drop it down in here. And I really thought that was a bad idea, primarily because I would be there all day. So I went ahead and put these numbers together, which is what I'm going to show you. Now he's got 6 feet of water in here, and I will be presenting this a little bit later on in a presentation to show how much volume he's going to lose when he fills this with rock. But the proposal is to drop a piece of pipe in here to act as a casing, fill this in with rock or gravel, and then seal this up with a combination of sand, bentonite, and I believe the top layer he's going to put in 3 feet of concrete up here and then more topsoil on top of it. Not sure exactly how he's going to be doing this. He's got somebody else that's going to be doing that. All I'm going to be doing is building the well screen for this. But let's look at what we have here, what we got to work with. We got 15 feet of water, and we have a hand-dug well that's 30 inches in diameter, and it's cased with concrete. What they would do, according to a fellow who lives out here, is they would find the smallest guys, and they'd set these concrete pieces down, and they would dig, and these things would sink down, and when they get to a certain level, they put another one on top, and they just keep digging and digging and digging until they got to the water. Tremendous amount of work. But at any rate, they have water, and in this case, this one filled up, and it has a static load of about 6 feet. Now granted, he only pumps maybe 1 or 2 gallons out of it when he's using it, because he doesn't have all that many flowers in a flower pot. But he wants to be able to get the water from here. Let's look at these numbers here. The volume of water is pi r squared times the height. So 3.14, it's 30 inches, so 15 squared, and we're going to keep all this in inches. You know, we're dealing with inches, we'll stay with inches. So 3.14 times 15 times 72, or correction, 225 times 72. It gives him a volume of 5868 cubic inches, or 29.4 cubic feet of water, which translates into 252 gallons. The proposal that I have for him is to drop either a 2-inch or maybe a 3-inch pipe down in here, schedule 40, because when you start putting all this rock in, there's going to be a lot of pressure on the pipe. and to bore holes of varying sizes, either say 3/8 to 5/8 of an inch, and then cover his casing with number 60 stainless steel, which is a mesh, a very fine mesh, so that as he fills it in with rock, the water will be able to come in. And in just a moment, we're going to deal with that aspect of it. The thing is, he's an older gentleman. I can sit there with a calculator and work stuff out for the next 3 hours, or I can write a computer program where he can just see the numbers for himself. But what he's concerned about is when the casing is put inside here, that he won't be able to get the water that he wants. That is not really a concern, because this thing has a static level of 6 feet. Now it's gone down to about 5.5 in some droughts, but it tends to hold 6 feet of water. It has never been pumped dry, so we don't know what the recharge is on this, or the drawdown as it's properly called. So what I'm proposing to do is to drop a piece of casing in here, a Schedule 80 or at least Schedule 40, with holes drilled into it, stainless steel mesh number 60, which he'll be purchasing, and he can put his drop stem in here with his pitcher pump up here, and then he can pull the water up because it's only 15 feet. So let's look at the next segment of this. Alright, let's go back to this and explain it out a little bit. Here's his water level, 6 feet deep. Then you have rock, sand, and gravel down at the bottom of it. Static water level is 6 feet roughly. If you hear some music, it's Sarah Brightman. I happen to like the woman. Alright, he's got 29 cubic feet of space in here that has to be filled in. 1 yard is 27 cubic feet, and 1 yard is about a ton. The gravel that he's going to need is only sold by the ton. So the cost is going to be $24 a ton. He's going to have to buy 2 tons of it, so it's going to be roughly $50 if he goes and picks it up. But he's going to have to buy 2 tons because it's only sold by the ton. So we know that we're going to need a little bit more than 1 yard to come up above this, and they always say add about 10% to it. I'm not worried about that. Right now, we just have to get this water covered by about a foot or two, because we know that that stuff's going to pack down under the weight of the material that's on top of it as a rule as it settles into this. We want large particle size so that the water will continue to percolate up into this. So let's take another look at what we have going on here. Alright, we've now filled this with rock. We started out with 29.4 cubic feet, and we had 252 gallons of water in this area that was available. And then of course we have the rock, sand, and gravel down here at the bottom. When we put the gravel into this, we lose quite a bit. We now have 121.3 gallons of water available in this space. That's it, because it's now full of pea-sized gravel, which is fairly small stuff. In addition to this, we also lose some of this water. It can never be drawn out because it's going to stick to these rocks, the rock surfaces. So let's say we pump that thing dry. We would continuously have water being dripped down, and it would be available to be pulled out if the pump was down far enough into this stuff. But he's going from 252 gallons to 121 gallons just by adding the 29.4 cubic feet of rock plus a little bit on top of this. I hope that you're understanding what's going on here. He is still going to have plenty of water for his plants, but he's losing a significant number. He's losing 48%, actually more than that, of the water because of the addition of the rock and the fact that the water, some of it, will stick to the rocks. So even if he were to pump it down, he wouldn't ever get all of it. In this presentation here, we have our 3-inch pipe. Now this is going to be filled with soil. Remember that? Because it's 15 feet from the water to the top of the land. So we have our 3-inch pipe coming down here. His question is, how much water can he get in here? Is he going to be working that pitcher pump and getting the water? So what I need to do is be able to explain to him, based on the size of the holes that are drilled in this, how much water is going to be coming into the casing. Now there's another side of this too. Where his pump is situated down inside here will determine whether or not he ever pumps down below this. It's not going to happen because he pulls like 2 gallons of water out of it. But he's concerned about that. So what I have to do is I have to explain to him how much water can get into this at the same time. Now this is 72 inches in length, but we're not going to do the casing for 72 inches because he doesn't want to buy the wire, the screen. So we're going to be doing 36 inches, and we'll be setting that a few inches off the bottom. What we'll do is we'll set a concrete block in here. We'll drop the casing into place, and then we'll start filling up the rock around it. And he's okay with that. He'll sit up just a little bit. As the water comes in, he won't be pulling in much sediment into his casing. But he wants to know how much water can get into this thing. So that is the next stage of what I'm going to show you in this development. Alright, I'm going to be using PC Basic. It's a basic computer programming language. I learned Fortran back in the 1970s and I used it extensively, but getting a Fortran program with a compiler on a PC proved to be difficult. So I went to using PC Basic. I forget what year it was when I bought a, you'd call it a tower now. So I'm going to be using PC Basic. We have a 3-inch piece of casing, and we have a 2.5 piece of casing. We want to divide it into 9 sections, and each section will have a line running down the length of it for 36 inches. And what we'll do is we'll punch holes starting at position 2. The first inch, there's going to be a band to hold the wire in place, the screen. So we'll go up, and then at 36 there'll be one, so we have 34 inches of space to play with. We have 360 degrees in a circle, and we want 9 positions because a 2.5 and a 3-inch pipe are both large enough to support that. You know, pretty good size holes in either one of these without weakening the PVC pipe itself. We take 9, we divide by 360, so each section is 40 degrees. So from 0, 40 degrees is 1, position 2 is at 80, position 3 is at 120, and so forth until we come back around. Makes it real easy to divide the circle, get our lines real nice and straight, and then once they're nice and straight, then come back in and drill the holes. Now what size is this guy going to go for? I don't know, but I don't want to sit here with a pocket calculator trying to show him how much water he can move. So we're going to use PC Basic, and I'm going to show you a program for that. This program is PC Basic, and it generates the amount of space that I get inside the casing as I drill different size holes from 1/8 to 1 inch. We've got the unique well situation, and we're using PC Basic. We're going to use a for-next loop. The for-next loop in this case is A equals some variable to another variable. In this case, A equals 1 to 10, next A. The program would look like line 10 for A equals 1 to 10, 20, print A, 30, next A. So what it's going to do is it's going to go for A equals 1 to 10, print A, 1, next A. For A equals 1 to 10, 2, next A. A equals 1 to 10, 3, next A. And so on until it gets to 10, and then it stops. It's called a loop. This is a very powerful function when you need to run a bunch of calculations over and over again, like I'm going to have to do for the gentleman who wants the casing in the well. Because in order for me to get paid for the work, I have to convince him that I know what I'm talking about. There's my program right there. For A equals 1 to 10, print A, see the little semicolon? That means space a little bit, print the next one. Next A, so it loops up to line 10. Type run. And back this off just a little bit. Back this off just a hair. Let me back this off just a hair. Hit enter. There we go. Printed it all out. And you saw how fast it printed it. So this shows you the power of using software, in this case a computer program. There are a lot of good languages out there. If you don't speak a computer language and you need to do multiple computer calculations where you don't want to use a calculator for hours upon end, this is the way to do it. So let's break into the next part of this. Alright, let's look at this. Line 10, and this is the hole we're going to drill in the pipe, is 0.125. It's 1/8 of an inch. We have our loop, so A is going to count up to 34, and each time it's going to increase the size of the hole that's being drilled in the pipe, and it's going to tell us just how big that hole is, right? So let's hit run and see what happens. The first time we drill the hole, it's 0.125, that's 1/8 of an inch. Then it's a 1/4 inch, 0.25, and it increases until we reach the very end, and then we have 4 1/4 inch holes worth of water being able to get in. But remember, we have 9 segments, so let's put that in.